You know, every single day, literally billions of us press a power button and watch a completely lifeless machine spring into existence. It's a little bit of everyday magic we totally take for granted. But behind that one simple action lies one of the most clever and fundamental solutions in all of technology. We're about to pull back the curtain on the computer's very first breath.
All right, so let's really think about this for a second. It's a genuine paradox, right? A computer's processor is just a piece of silicon. It can't do anything without instructions, without software. But how do you load that first piece of software if there isn't any software already running to do the loading? It's the ultimate chicken and egg problem.
And that's exactly where we get the term booting. It's short for bootstrap load, and it comes from that impossible old phrase, to pull oneself up by one's bootstraps. The very first computer engineers knew that's what they were asking the machine to do, to perform this seemingly impossible feat every single time it started up.
So to solve this impossible problem, the pioneers of computing didn't have some elegant software trick. Nope, they had brute force and a whole lot of patience. Let's take a look at the sheer manual labor that went into giving these early machines their first thoughts.
I mean, look at this. The very earliest machines, like the famous ENIAC, didn't even boot like we think of it. You programmed it by physically rewiring it with a bunch of cables. A few years later, you had machines using mechanical switches to slowly read a program from paper tape. By the 50s, things got a little easier with the IBM 701. It had a load button that would read one single punch card. But even into the 1960s, with computers like the PDP-8, operators had to physically sit there and flip an entire panel of toggle switches one by one just to key in the first few instructions.
And here's the key thing to understand. That first little program, the one entered by hand, it was incredibly simple. It had one and only one job: to act as a stepping stone. Its sole purpose was to tell the computer, hey, go look over there at that paper tape or that magnetic drum and load the real program from there.
In this quote, just brilliantly sums up how intense that was. Imagine it. You're keying in a program, one single bit at a time, using a long row of switches. If you flipped just one switch wrong, just one, the whole thing would fail, and you'd have to start all over again. It was slow, it was tedious, and you had to be perfect. There just had to be a better way.
And thankfully, that better way did arrive, and it came in the form of a revolutionary new piece of hardware. This right here was the invention that truly solved the bootstrap paradox once and for all, making computers practical for everyone.
Okay, so this slide gets to the absolute heart of the solution. It's all about two different kinds of memory. Your computer's main memory, its RAM, is volatile. Think of it like a temporary workspace or a whiteboard. As soon as you turn the power off, poof, everything on it is gone. But read-only memory, or ROM, is non-volatile. It holds on to its information forever, even with no power. It's the computer's permanent long-term memory.
So by putting those first critical bootstrap instructions onto a ROM chip, literally everything changed. All of a sudden, that first step was permanent. Manufacturers could ship computers with the startup program already baked right in. No more flipping switches, no more feeding it punch cards. This single innovation is the direct ancestor of the simple power button we all use today, and it was absolutely critical for turning computers from these massive lab projects into products you and I could actually buy and use.
So that's the history. But how did that basic concept evolve into the incredibly complex, lightning-fast process that happens inside your computer today? Let's trace the modern chain of command.
Today, we don't just call it ROM. The modern term for these permanent instructions is firmware. It's the software that's permanently etched onto chips right on your motherboard. And you've probably heard of the two main types: the old-school BIOS and its much more powerful modern replacement, UEFI.
The key idea here is that modern booting is something we call a chain load. Seriously, think of it like a software relay race. When you hit the power button, the firmware wakes up and does a quick hardware check. Then it finds your hard drive and loads a teeny-tiny first-stage program. That little program's only job is to hand the baton to a slightly bigger second-stage program, which we call the boot manager. And that boot manager finally has enough power to load the core of your entire operating system, the kernel, which then takes the final baton and runs with it, bringing you all the way to your desktop. Each step hands off to a more powerful successor. It's beautiful.
And the firmware that controls all this has gotten a major upgrade over the years. The old BIOS was pretty basic. It just knew to look at one specific spot on the hard drive to get started. But modern UEFI is way more sophisticated. It's almost like a mini operating system itself. It's way more flexible, it can handle gigantic hard drives, and, as we're about to see, it has way, way better security.
Right, because when you have a process that's this fundamental, this important, it also becomes a huge target.
Protecting this first digital breath is one of the most critical jobs in all of computer security.
So what happens if that delicate, carefully orchestrated chain of command gets broken? Whether it's just a simple software glitch or a full-on malicious attack, the consequences can be, well, pretty disastrous.
One of the most common failures is something you might have even experienced yourself, the dreaded boot loop. This is when your phone or your computer gets stuck. It tries to start up, fails somewhere in the sequence, and then restarts to try again, over and over and over. It's incredibly frustrating, and it can be caused by something as simple as a bad software update.
So to prevent these kinds of problems and attacks, modern systems build what we call a chain of trust. It's a fantastic concept. Technologies like UEFI Secure Boot will only allow approved digitally signed software to run during startup. There's even a special hardware chip called a TPM that can check and verify that nothing in the boot process has been tampered with since the last time you used it. It's all about making sure that from the very first instruction, your system is secure and running only the code it's supposed to.
And this quote just brings us right back to where we began, to that central paradox. That some mechanism they talk about, well, it's the entire elegant solution we've just walked through, from clumsy toggle switches and punch cards all the way to the secure, permanent firmware that's baked into every single machine we use today.
So the next time you turn on your computer or your phone, just take half a second to appreciate that invisible, lightning-fast sequence of events. You're not just turning on a device, you are literally witnessing the culmination of decades of brilliant engineering that solved a problem that once seemed completely impossible.
We have gone from minutes of tedious manual labor to an almost instant-on experience. The whole boot process has become so fast and so reliable that it's practically invisible to us now. But as our devices get even more complex, more powerful, and more interconnected, you have to wonder, what will the next evolution of booting look like?